Okay, it's recording.
Okay, so welcome to the 15th talk of the categories seminar. So this time we are kind of moving in a kind of a different direction, maybe some sort of a digression. So instead of talking about Grothendieck's base change formulas and Quillen's theorem A as in Cisinski, so yeah, it's meant to be a bit of a digression. So I'll be talking about generalization of theorem A. There is a two-categorical version of Quillen's theorem A, and so it will be two parts. So today I'll be just so there are two parts of the talk. So today is the first part, and today the plan is to talk about the idea and the motivation for thinking about a generalization at the first place, like why do we need a generalization, right? And then I'll talk about some basic two categorical stuff, right? I'll just introduce some of this. So yeah, this is the first part is mostly definitions and a few results. So yeah, so it's mostly definitions. So just laying the grounds, laying the foundations for the next talk, and where we'll state the more general theory that we have. And yeah, at the end, so yeah, this is my aim. I also wish to talk a bit about infinity localization. So maybe, so if I'm not wrong, maybe it's probably the 7th chapter of Cisinski. So okay, so first, okay, let me begin. So I will talk about. So yeah, I will also talk about a reformulation. I mean, so a way we can redefine. Restate Quillen's theorem A. And before that, let me write the classical version that all this now found. Right. So this is the one that everyone's familiar with. So I'll start with this, and after that, I'll talk about the version that I am interested in. So as mentioned, as written, so maybe I should mention this. This is work by Garcia and Stern. Yeah, I'll link the references. You can find the links in the web page. Okay, so yeah, the Quillen's theorem A in all its glory. Right, so first, okay, so let me fix. So C and D categories. So this is my category of categories. And you have a functor from C to D. Then for all objects X of D, the geometric realization of my bad. The geometric realization of yeah, so let me write this. Right. Of the comma category, right? So this is okay. Wait, let me write this properly. So wait, it doesn't look like an X. So yeah, I mean this to be an X, right? Of the comma category. So is constructible. Then it follows that we get a weak homotopical. So this is the classical version that we are familiar with. Right, so I will talk about a way to think about it a bit differently, which is an equivalent, but that kind of gives the motivation away, right? There's a weak homotopic equivalence. Okay, so this is the classical version that you have. So okay, so yeah, maybe. Right. So yeah, let me talk a bit about that. So in context of homotopy polynomials, so this criterion that we have, wait, let me yeah, sorry, yeah, this criterion that we have like this of Quillen's theorem, then this is like so this is about this thing that we have this right. So it is right. Let me step back for a moment and make sure. Yeah. So it is about, you will see that it is in a way it is related to homotopy cofinality, right? So what do I mean by cofinality? It is like so something is homotopy cofinal when you restrict all the diagrams along it, then and it preserves the homotopy colimits, then it is said to be homotopy cofinal. So that is what I mean by saying homotopy cofinality, right? So yeah, what is the point of generalization, you may ask? Like, why do we care? What is the motivation? So yeah, it is like right. So it kind of gives us a way to work with the classifying spaces, right? So, but in many situations, it is more desirable to recover the associated fading, right? So that is in a way the point. So now let me restate this the Quillen's theorem. So another version, a version. So this is equivalent, but this will kind of give away what I mean. Quillen's theorem A, right? So, right, again, let me fix one categories. So suppose X and Y are one categories. Right. And you have a functor. Again, you have a functor. You have a functor between these categories. Then, if for all objects, okay, it's okay. My bad. So this is right. Okay, I messed up with the notation for a moment. Right. I don't know if I can get rid of this thing. I can't access the erase in this case. Actually, let me move it to here. Okay. So yeah, so right. So yeah, X and Y instead, which is CD, right? So XY. So X, you take an element X of Y, then right. If for all such elements X in our category Y, if there exists another element, so let me call it X dash. So in X, this is bad notation, but okay, let's stick with me for a moment. And map, you have this kind of map. So this map takes an X to F of X dash, and every morphism. So all the morphisms that you get in this way, so F of Z represents an initial object of this category. So we take the code. Again, sorry. This is X, okay, right. We pause for a moment again, just to make sure. So yeah, you are taking the core of this category. Apologies. So I think I should get rid of this now. Yeah. So right, objects of. Right, you take the code, then this you'll get this to be a homotopic equivalence. Right. So this is another version. I'm not sure how can I add an extra page.
At the bottom left, there should be the arrow that says plus.
Okay, makes sense. Good, thanks. Thank you very much. Wait, let me set the zoom. Oh, yeah, this is fine. Okay, right. So, okay, yeah. Let me say this again. Right. So, so it is like the motivation. So yeah, why do we care about this version? So it is like um, so
Could you
so
scroll
we
up?
are kind of
Sorry, could you scroll up so I could see the? Yeah, thanks.
yeah. Sorry. Yeah. So yeah, the point is that we are in a way looking at the infinity group codification of this null, right? And that is very much like the infinity localization of that of the category with all the morphisms. So roughly, really roughly, naively speaking, that's the idea. And then we can we'll see how we can formalize this in the second part. So yeah, this is it's like a standard tool in higher category theory, theorem A. So that is like so in a way we can see from this definition and from the classical definition as well. So the standard version that we have, so it is about strict one categories that implies something that lets us conclude something about infinity zero group points, right? So now, so we can, instead of looking at one category, strict one categories, so our aim is to have a version about strict two categories from which we can get some sort of equivalences between infinity one categories. So that is the motivation, right? So we'll see. So we'll define marked two categories later. So instead of strict two categories, we are interested in these versions called the marked two categories that we'll define next. So okay, let's move on to the next section then. This is just some basic two category theory. All right. So yeah, first let me fix a few some notation for convenience. So yeah, so this is two cat is my. So this is strict two category. I mean, so two category. Yeah, this is the category of strict two categories. Wait. Wait. This is the category of two categories, right? And so throughout this talk, so when I say a two category, I mean a strict two category, just some abuse of notation. So let me write this down. So two category would mean I don't know. Means strict two category. Similarly for the two functors. Right. So okay, now let me do some notation. Right. So X is a two category. So this is as I said. So this okay. So C will be in uppercase because this is my category of two categories. So this is just this means or two category. I should be a bit careful about this. Right. So X is a two category. Then the one morphism dual. Again, you can find this is standard notation that is used in the paper and Garcia and Stern's paper. Right. So one morphism dual is denoted by right. So two morphism, similarly, two morphism dual is denoted by right. And the dual that reverses both one and two morphisms. One and two both. So one and two morphisms is denoted by. So I will need this later. You'll see. Right. So okay. So now we'll talk about, I'll introduce the notion of a normal X to functor. So starting off with the definition. So as I've said, most part of the talk will be mostly talking about definitions and results. So so the first part's going to be kind of monotonous, maybe. So yeah, so X and Y are two categories. And so a normal X to functor. Again, I'll just call this an X, normal X functor, or just the X functor, right, from now onwards. So, okay, let me call this F from X to Y. So it has the following data, right? So you have a map. We have this map, and for all pairs, so let's see how this is definition, how normal X to functor is different from just any two functor. So you have, we'll see that there's a notion of this compositor. So for all pairs, so if we use some messy notation because I like it. For all pairs, you have a functor. Right, and for all triples, again it will get a bit more messy maybe. Satisfying. I need a bit of space. So yeah, it's going to get a bit messy. So I hope I don't miss. This is our composition map. Right. This is the image on the functor. Okay, you do this. Just applying the functor, there's nothing special I'm doing, and so let me call this sigma. You have this natural transformation, sigma. There exists natural transformation. So, yeah, for all for all triples, so you have such a natural transformation. There exists natural transformation sigma such that this type of approach. And yeah, it is called a compositor. Cool. Such that you have a bunch of axioms. All right, for all axioms. Okay. Most importantly, the compositor satisfies the hexagon identity. Hexagon identity. And this, I hope I get this right. And this. Right. So yeah, that's the definition. Now again, some the notation. So this will be so this is a category of two categories with normal x two functors, right? So this is a category that we have. So now, right. So now, yeah. So now we'll briefly talk about the Duskin now. That's a two categorical version now that we are familiar with. So first, let me introduce. Let me talk a bit about co-simplicial objects that we get in this category that we have, and cat. So yeah, we get a co-simplicial object in cat. So we compose these things. So we compose this co-simplicial object in cat. By composing this with this inclusion. Right. So yeah, we denote just okay, let me call this something. Let me call this J. So again, so this is an abuse of notation. We denote so right. So right. So then yeah. So we get a functor using this co-simplicial object. And this precisely the Duskin now with, so yeah, I'll just call this N2. Right. So this is called the Duskin now. Right. So yeah, now I'll define an analog of what we saw previously. So yeah, let me define this first, then I'll talk more about it. So suppose I is let I be a linearly ordered finite set. So then let's define a category of I. So here in this category, the objects are elements of I. Straightforward enough. And right, and the category of morphisms that we have. So here, yeah, x and y are elements of I. So it is defined as a poset of finite x. Defined as a poset of finite sets, such that yeah, the minimum element is x, and yeah, you have ordering by the inclusion, which is understood, I guess. And the composition is given by again we take three elements of I. This is the composition rule. Right. Okay. Again, there's more that I'll kind of be assuming again. So notation. So yeah. So if I just take this product, and I'll just denote this by n, just right. So yeah, I'll just get rid of the brackets. Oh, I mean, yeah, it's just a bit of a hassle. So yeah, so this is the notation that I'm using. So right. So right, so it is. So we can say we can clearly see that this ON forms a co-simplicial object in the category of two categories, which we can denote by so the co-simplicial object will be denoted as like this, right? And yeah, again we kind of use a bit of abuse of notation. So we call this composition that we have out. So I think I don't need to add pages. It seems to work like this. So remember this. So this is a co-simplicial object found by this category. So again, for brevity, we call this composition to be this. So let me write this formula. The composite is so okay. So now again, now we have this notion of lax functor. Now for all we can define. So these are these lax functors that you have. Define. So okay, let me use this. Defined on. So yeah, so on one morphisms. So this is the way to find it. Right. So this is the way to think about it. So right. So okay, let me quickly state a few properties of this skin now. So I'll call this a proposition. Yeah, I won't be proving anything. So again, you take two category X, and then so N2 is fully faithful. Second. Then this lax functor, the lax functor forms a natural transformation of the co-simplicial object. Right. And we get this, so we'll have a bijection. Okay. So the lax functor that induces, so that I've already defined this, induces a bijection. So yeah, Y is an arbitrary two category. Oh, sorry. Right. So yeah, just a few properties. So now let me talk about lax slices and functoriality. Maybe the next section. Maybe switch change to the next page. Lax slices and functoriality. So I'll begin by defining what I mean by lax slices. So again, so X is a two category, and you have an object in the two category. So let's define. So you define a two category, which is called the lax slice category. So this is the notation as follows. So objects of morphisms with source X. Excuse me, I'm sorry. Okay, yeah, morphisms with source X in X, and morphisms are, sorry, morphisms may be formed. So it takes objects. Right. So yeah. So maybe yeah. Consists of. Yeah, consists of homomorphisms here. I have a morphism from Y to X in the category X, of course, with the two morphism. U to U composer. So here, so this is my U. I'll call this U, this map, right? And what are two morphisms? Two morphism from these morphisms. So let me write this as pairs. So UB, so here's the U, here's the B. So similarly, let me forward the one to UB and alpha. So this also consists of two morphisms. So let me suppose eta U to V such that the following diagram commutes. Right. So yeah, similarly we can define, okay, let me write this. It's important. So we can define the oplex slice category. So we just term, so yeah, it is like switching the directions of the arrows. That's the two categories. So here's the construction. So you just play with these dual objects. So this is where the notation that I'd introduced comes in handy. Right. So this is the way we define the oplex slice. Right. So yeah. So you can see that we have. So again, I'll skip the details. So we get a functor. So we get a functor. So yeah, this is the category of pointed flags. I mean, yeah, pointed ones. So the pointed version. So LCAT is a category of two categories where you have these right normal lags to functors between the categories. So it takes two. So you can check that. Yeah, you get a functor. So I think I have 25 or 25 minutes. So yeah, I don't know. So yeah, let me talk about. I have time. Let me talk about infinity localization. So I was not sure if I could reach that far, but so infinity localization. So again, so it's like I think if I'm not mistaken, so it's probably the 7th chapter of Cisinski. So maybe let me check this. Yeah, this is on the 7th chapter. I just checked it. So here we'll define our main objects. Like here now in this section here. And let me not have a separate section. Let me define it in this section. So I'll define what I mean by a marked two category. So the way we'll have our version two categorical as we saw before, so the idea is to have a version for marked two categories. We have one, the classical one is for strict one categories. So instead of strict two categories, we want marked two categories. So yeah, I'll just define marked two categories and a few things and then talk about localization in this section. So a marked two category is a pair. So my dagger may not look like a dagger. It may look like a plus. I need to use a dagger. Right. So it is a pair where X is a two category. And you have this collection of morphisms. of x, and these contain all identities, containing all identities. So yeah, at some point, okay, let me write this and say what I want. All identities. Yeah, at some point we'll see why. What is the point of this collection having all identities? Maybe that'll be part of the next talk. I mean, yeah, we'll see this. So, right, a functor, similarly, we define a functor of marked two categories. So, let me call this again. Is a two functor. So, there is a two functor from x to y such that, right, so this is so, okay, now let me introduce some more notation. So, yeah, as you've been seeing so far, if you have stuck around so far, so it's mostly been defining stuff so far. So, yeah, most of the action, as I said before, will be on the second part of the talk. So, right. So, yeah, the notation. So, data. So, it's a category of marked categories. Right. So we'll see now that. So yeah, this is one of the neatest parts of the theory of marked two categories. That the way we see categories with weak equivalences and homotopical functors in their language. So maybe your definition. So you can define a category. So yeah, we'll see a category with weak equivalences. So this is what I mean. So this is my notation of weak equivalences, just short version. Is a pair. Okay, so but yeah, maybe I shouldn't have used this notation, but okay, let me stick with this. So here x is a one category. So yeah, don't confuse this with the previous notation that I. So yeah, that stays in it. So now this is the point of this is to, yeah, from this version we will define a two categorical version. So first I am just doing things one categorically, and right, and this is a wide subcategory. Right, and similarly, let me like this homotopical functor. So again, for this definition, we are sticking to this notation. So sorry, I should have not put it. So it is a functor from x to y such that it maps from x to y. Right. So yeah. So now analogously, two category with weak equivalences. So maybe y plus, and this is the notation that we defined before, consists of two category y with the structure of a category with equivalences. Weak equivalences. So yeah, it just has the underlying structure, right? With the structure of a category with weak equivalences on the category with weak equivalences on the underlying one category. Maybe I should add a page now. Underline one category. Okay. Right. So similarly, we define homotopy. And so as we have a homotopical functor, we can similarly by the fact that we just take the underlying one category to be a underlying one category to structure to be a homotopy functor, let's say. Right. So okay, now let me introduce notation for another category. So yeah, I'll use this notation in the next part without mention. So I'm making sure that I'm writing everything properly. So okay, so this is a category of two categories with weak equivalences. Weak equivalences and homotopical two functors. So we get another category. So let me move to the next page. Right. So now I define what I mean by a two category to be a marked two category rather to be saturated. So let me consider a marked two categories. So X is called saturated. If so, there are three things must happen. So Wx must contain if contains all equivalences X. Secondly, this category, or maybe this should be the second one that I'm writing should be the first one, but anyways, so this is should have written this. So two categories. So this is the first thing that should strike our minds. And now for F, you take morphisms F and G in X, right? And we have an invertible two morphism. Then G, right? So yeah, this is what I mean by saturation in context of marked two categories, right? Okay, so now another definition. So for a functor of marked two categories for all for y, okay, becomes y, we can are there more people? No, there is. We can right. We can define a marked two categories follows whose underlying two category is a like slice category. So yeah. Oh, sorry. Thanks. Slice. Right. And with right, not just that, so to define what are the markings, like so-called markings, with an edge marked. So yeah, let me write this explicitly. If the associated two morphism is invertible and the associated one morphism is marked in. Right. So yeah, I still have 14 minutes, it seems. So yeah, now maybe the last thing. So yeah, now I'll just define what I mean by localizations. Turn to localizations. So now, right. So similar to the notion of marked, we had this notion of marked two categories. We similarly have this notion of marked simplicial sets. More about which I'll talk in the next part, maybe. So we begin by choosing a marked simplicial set. So we use a similar dagger or plus notation, whatever you like. Right. So an infinity categorical localization X by W is an infinity equipped with the map. So, okay, what do I call it? Let me call it theta. Okay, so because chi looks really confusing, chi will look like an X. And the category of marked simplicial sets says that for all infinity categories, so yeah, this is a category of infinity categories. So the map, so yeah, if you just pass on to the function categories. So this map is an equivalent, would be an equivalence of infinity categories. So, okay, I see. So, write this properly. Wait, sorry. I don't know what the problem is. Oh, wait, excuse me. Of this, what happened? Yeah, my bad. Okay, yeah, is an equivalence of infinity categories. Right. So now let me state a result from Cisinski. So I have to check. I mean, yeah, I can just refer to it without saying which where it is, without stating the exact number, but let me sure. Yeah, this is 7.1.10. So, right. So again, you have this marked simplicial set. So this localization that you get is cofinal coordination. So what do I mean by cofinal? So cofinal functor is like let me write this. So what do I mean by so at co-initial is just a dual version. Cofinal functor is like so you take this functor such that precomposition with so I think we have talked about this before, but yeah, precomposition with X preserves infinity polars. So that's what I mean by cofinal, and so co-initial is just dual version. Right, so I still have a few minutes left, but yeah, let me stop here. And so let's continue for the other part, the second part. So yeah, I'll stop here. Thanks for listening. So maybe you can stop the recording now.